right, so while we are doing our static collection, we also need to collect some field notes. We need a log sheet for the session that we're collecting. So we've already pre-filled some of this for our work here at sea. It's a GS14 antenna. It's a CS20 controller. The software version is here. Thinking about using this data or coming back to it after a number of months or years, you need to have this kind of information captured in case you end up with an issue with a client and a potential lawsuit. So this is part of protecting yourself. The kit number we're using today is number 1. We just have numbered our kits. You may ordinarily put the serial number of the unit in here instead. But kit number 1 works for us. The project name here is Midterm Winter 20. So the winter semester of 2020. The project number, I'm going to call this project number 1. My station name here is going to be spruce, because I have a spruce tree right behind me. My station number will be 15, so that's going to be the point number. My 4-character ID, I'm going to call it SP15 for spruce 15. 4-character IDs are used for Rhinex data files, so if we had to export this into a generic format for processing with other software or submission to Natural Resources Canada for post-processing, then we would use the 4-character ID on the Rhinex file. The date of our survey is March the 4th, I believe. It's our first observation session on here. The operator is Lee. And our collection rate was set to 1 second, even though I didn't show you that to start with, although we can take a look at that later. Our start time, day and time, is March the 4th at about 14:54, I think, about the time I started, and 16:54. That will be encoded into the raw data in case you happen to make a mistake on it here. My 24-hour clock glitched. All right, so we're going to be looking for the latitude, longitude, and height, or northing and easting and height if we have a coordinate system attached. It, by default, can give us lat, long, and height. Possible obstruction or interference sources here are the spruce trees, and we will do an obstruction diagram to go along with that. General weather conditions, I'll have to check on that. It's a little bit windy, sunny, and we'll get a temperature. All right. The antenna height at the beginning of the session was 1.142, and we'll measure that again at the end of the session to see whether, to make sure that it hasn't sunk into the ground or nothing has changed in between. All right. Okay, so to get that receiver position, I get the controller, and that information is available here at the top of the screen. So we're continuing to log the raw data. We've counted up now 450 points. We've been here for 7.5 minutes. Now here on the top of the screen are the other things that I wanted to look at. So from what we see right here, we see a radio icon, and that tells us if we touch that when we're not in the measure application, we can change the channel through that. If we touch it right now, it will tell us if we've received any raw data, RTK data. That would be the radio corrections from a base station. And we made sure we were not getting any corrections for this static collection job. The 2D and 1D are the quality. That's the coordinate quality in 2 dimensions, or horizontally, which is about 1.97 meters right now. And in 1 dimension, which is about 2.6 meters. Vertical is always worse than horizontal when we're dealing with GPS because the satellites are all above us. Our horizontal is pretty good, our vertical not so much. because we have nothing down near us to create good geometry in that direction. We're seeing currently 10 satellites, and if we touch that, it will give us more information. So we have 12 visible, 10 are being used, 5 of them are GPS, and 5 of them are in the Russian or GLONASS system. When we look at the satellite tracking here, we can see the list of our GPS satellites. So vehicle 17 shows us an azimuth for where it is in the sky, and that we have L1 and L2 signals being received. We can see our GLONASS satellites as well, same information. We can take a look at the sky plot and see where those satellites are. So the ones down around the edge that have black over the numbers, white numbers and black backgrounds, are too low on the horizon to be used. We've set a 10-degree mask. Anything below 10 degrees gets filtered out. There's too much atmosphere to interfere with the signal. The ones with the white, those are the ones that are being used or are available or being used in our solution. All right, so that was our satellite tracking. I'm going to go OK and get out of that. Going back to the satellites here, we can also take a look at our data logging. And this is the logging on board here. So we're logging in Leica format onto the controller here, not into a card on the antenna. Static is our dynamics. We're sitting still. We're not moving on a vehicle or walking around. This shows the observations, this current observations being logged, and no points yet because we haven't stopped and stored the point. The point occupation shows us that we're static. The GDOP has now gone up to 2.2. Our logging rate is once every second, and we didn't set a stop time, so it's not showing us how much longer we'd have to wait. All right, so going OK on that. All right, and the other thing that we want is here the position. So that big circle with the open center means it's an autonomous position, just a code-based solution. So about 1% of 300 meter signal wavelength. So 1% of 300 meter wavelength is about 3 meters. And so that's about the best we could expect out of this. The position shown here is northing, easting, and height. So I do have a coordinate system attached. I see negative numbers on my easting, so it's a 3-degree transverse Mercator projection that's been attached to this. So I would write this down then on my sheet. You'll see the numbers are continuously changing there, and they will. So I can round this off to the nearest meter, and that will give me a good estimate of the position here. I can't get better accuracy than that right now. And we will get millimeter level accuracy when we post-process this data, but for the initial observation here in the field, it's the same as if you had your phone or a handheld device, and it's meter level accuracies.